Let's go for the third speaker of the afternoon. So Lucas Reis from the University of Federal University of Minas Gerais, and he's going to talk about the special points on curves using Finitos. So,
can I start?
Yeah, you can start when you want.
Okay. So first of all, I'd like to thank the organizers for the opportunity to talk. I have the feeling that this event has been incredibly successful, especially the tribute to Fernando Torres. And so in some ways, I would just include curves in the talk. It's not the main object. It goes back to similar things that we have seen Alonso's talk. So I think I will be able to speak some slides. Just to start, we just fixed some notation for prime power Q. FQ is the finite field with Q elements. FQ star is cyclic, right? The multiplicative group is cyclic. Everyone knows that. And any generator of this cyclic group is called primitive element. So as we have seen Alonso's talk, we also have a character sum formula for the indicator function of primitive elements. This is due to Vinogradov. And actually, after this formula from Vinogradov, Kalitz obtained a character sum formula for elements in finite fields with any prescribed multiplicative order. So it's, in some ways, it's just a generalization of Vinogradov's work. Since Kalitz, we have this kind of generic problem that is proving the existence of primitive elements in finite fields with additional properties. And so just to give an example, this is the most famous example that Alonso also have mentioned. The PNBT theorem ensures the existence of a primitive element in any extension or any finite extension of finite fields, right? So there is a partial result of this theorem from Kalitz, and we also have the complete result from Davenport when Q is prime. And also the complete proof is finally given by Lenster and Scoof in 1986 with the help of computer calculations. And finally, Cohen and Huzinska in 2003 gave a computer-free proof of the PNBT theory. So this is just the initial motivation, the existence of primitive elements with additional properties, but the focus of this in the motivation part in this talk is the problem of finding pairs of primitive elements. And so the general setting is we just consider a rational function with coefficients in FQ and try to prove the existence of a primitive element alpha such that f of alpha is also primitive. So we have this pair of primitive elements, alpha and f of alpha. F is a rational function. So here we have, I think, the most, four of the most relevant works on this problem, right? Just to give a few references. But now we just observed that finding pairs of primitive elements in this setting, alpha such that f of alpha is also primitive, is the same as considering points on this curve defined by y equals f of x, whose coordinates are primitive elements of fq, right? So this is the main motivation. We can see this problem of pairs of primitive elements as just points on this curve whose coordinates are primitive elements of fq. And so for me, at least, a natural way to extend this problem is to consider this kind of curve and ask the same question, right? So we consider curves y to the n equals f of x, and we just want to find rational points with primitive coordinates. So first remark is quite trivial. We can assume that n is a divisor of q minus 1. And so it's just a simple exercise. So basically, if n divides q minus 1, finding a rational point with primitive coordinates is equivalent to find alpha in fq primitive such that f of alpha has multiplicative order q minus 1 over n. So and which is also called n primitive element. This is just a terminology I introduced in a paper in 2018, and people are using. So you can also find this terminology. N primitive element is an element of order q minus 1 over n. Okay, so basically we're just taking a variation of this problem. Instead of pairs of primitive elements, I want an element alpha to be primitive such that f of alpha has some order, q minus 1 over n. Okay, so just going to the tools, right? Alonso also spoke about this. But the main tool for describing the primitive elements is the concept of freeness. I will just give quickly the definition. So for a divisor G of Q minus 1, an element in FQ star alpha is D3 if alpha is not of the form beta to the E for any E dividing D such that E is greater than 1 and beta is in FQ star. And so from this definition, primitive elements are just Q minus 1 free elements, right? So I'm taking G equals Q minus 1. As I said at the introduction, we have a character sum formula for G3 elements. So I say it was primitive elements, but it is more general. So we can, we have a character sum formula for the indicator function of G3 elements. So it's right here. We have the Möbius function, Euler's phi function, and also here we have the sum of characters of order T. So T is varying over the divisors of G. And so considering this formula, we have something more general obtained by Kalitz. We have this is the characteristic character sum formula for the characteristic function for elements with order capital N, right? So we have these. There's just one difference between these sums. Here is the sum of all the characters of prescribed order T. And here we have the characters of order dividing some number, which is a divisor of Q minus 1. But basically, we can reorder the terms here in the characters according to the orders. And so we obtain from this first formula, we can obtain this second one. And so it appears this function Tn. Tn is just T over the GCD between T and N. Just to finish the motivation, we observe the following. If we pick an element alpha in FQ star, we observe that this element has multiplicative order capital N, if and only if alpha is of this form, beta to the Q minus 1 over capital N, but it's not of this form, right? So beta to the same power, but now times D, with D divides capital N, and D is greater than 1. So motivated by this description of elements with order N, we basically extend the concept of freeness. So it can be defined for any cyclic group. We have a capital Q here, positive integer, CQ is a cyclic group of order Q. And so for a divisor N of Q, and now a second divisor R of Q over N, we state an element H is Rn3, so we have two parameters now. This element is Rn3 if these two conditions hold. So the first one is the order of H divides Q over N. This just means that H is in this cyclic subgroup. And the second one is that H is R3 in this subgroup. So we just basically taking the original definition of freeness, but now we are looking locally, right? So we take a subgroup. So H is R3 in C Q over N, which means that H cannot be written as G to the S with G in this subgroup and S dividing R if S is greater than 1. Okay, just to see the relation between the original definition of Reis and this new one with 2 parameters, we observe that if n equals 1, we just recover the definition of R free elements. And also we can describe elements with any prescribed multiplicative order by means of Reis, right? So if n is a divisor of Q, the elements that are Q over n and 3 are just the elements of multiplicative order Q over n. Okay. So basically, we can obtain a character sum formula for the elements that are R and 3. So this is the formula. You see that it appears the same arithmetic function we obtained when we just simplified Carlet's formula for elements with prescribed multiplicative order. And the main idea to prove it's something traditional in this kind of issue. We just use multiplicativity on R. We just essentially we take the prime factorization of R, and so we can obtain this formula. Just to notice, right, as we have observed, the elements of multiplicative order Q minus 1 over n are just the Q minus 1 over n and 3 elements. And so we just plug these 2 values in this formula. We just recover the new Carlet's formula, right, from the simplified version of this indicator function. Okay, so going back to the problem, right? The primitive points on rational points on curves y to the n equals f of x with primitive coordinates. So as we have seen, we just reduced the problem to prove the existence of alpha primitive such that f of alpha has order Q minus 1 over n, right? So as we have seen, we have the characteristic formula, characteristic function for the elements with order Q minus 1 over n. And basically, we can work with something more general. So we just have here a pair of polynomial values, right? So x at alpha and f at alpha. And so we just work with pairs of polynomial values with prescribed frames. By this, I mean, we take a pair of polynomials, f and capital F, and consider the number of pairs f of y, capital F of y with y in fq, such that f of y is Rn3 and capital F of y is capital R, capital N3, right? So we have 4 divisors of Q minus 1 here. So just a quick remark, it's only interesting if Q minus 1 is not a prime. So we assume that Q is at least 5. So in this kind of multiplicative dependence, we have this number can be 0, the number of pairs f of y, capital F of y with this property can be 0 if we have some multiplicative dependence between f and capital F. Here is an example. I'll go much into the details, but we just use quadratic residues in FQ. There is a counterexample. But we can avoid this kind of thing if we assume this condition, which is not too restrictive. If we assume that f and capital F are non-constant square-free polynomials such that the quotient f over capital F is not a constant, we can avoid this kind of multiplicative dependence. And it turns out that asymptotically, this condition is also sufficient. We have here the theorem. Well, it says a lot of things, but basically we want pairs of primitive elements with prescribed freeness. And so if we assume that this condition, right, f and f are non-constant square free and the ratio is not a constant, we can get a nice estimate for the number of pairs with prescribed fringe. So this is the estimate. We have an error here. Age is bounded by this function. And so this is quite traditional. We just employ the characteristic functions for freeness, and then we employ Weyls bound. And basically, this condition on the pair FF is just to employ Weyls bound effectively. Here's just a remark. In a proof using Weyls bound, we can get something milder than the condition we impose on F on F. And basically, we can obtain many pairs of polynomials that are not square free, but still the theorem holds. But this is not much important. So just to finish out the application, we want to find points on curves with primitive coordinates. So essentially, in the application, we wanted to obtain effective results. So we just consider elliptic curves. So y squared equals f of x, and we want points with primitive coordinates. So we further call fq primitive point of C. And so considering y squared, we just want alpha to be primitive such that f of alpha has order q minus 1 over 2. So q is odd here. And basically, as we have seen, f of alpha must be q minus 1 over 2 to 3. So essentially, we just employed the theorem, the main theorem here, with the parameters we want. And so we obtained the sufficient condition. And also we obtain a sieve method of this. This was initially developed by Cohen and Huzinska in 2003 paper. I'll also talk a lot about the sieve, right? So I'm not going to give all the details, but we can obtain some slightly better estimate after this corollary. And so combining this corollary estimates on the function W, I'll also talk a lot about the details. I'm not going to describe again. And we also use computational tools. We obtain some numerical results. So the first one, if Q is at least this large constant, odd, and so any elliptic curve has an FQ primitive point. And also for this special family of F, we only need Q being, well, slightly smaller than the first constant. And so actually at the end, we just focus on this special case of F being of this form, x cubed minus ax. And actually for a equals plus or minus 1, we obtain very interesting results. So Q is an odd prime power. And so we always have FQ primitive points on elliptic curve C1, so a equals 1, or C minus 1, a equals minus 1, unless Q is one of these constants, and these are genuine exceptions. And so motivated by this case of this special F, x cubed minus ax, we just propose this conjecture. So we take Q, an odd prime power, and just exclude all the guys here in these two lists. If Q is not here, then this curve CA always have an FQ primitive point. Actually, we have some data based on that. We can prove that this conjecture is true for Q up to this inferior limit of the interval, and after the upper limit of this interval. Here in between, we cannot say anything, basically. From Q, from 0 to this inferior value, we can go straight up to computer calculations. And from this upper limit and above, we can prove mathematically. But from Q in between, we don't know what's going on. And basically, the conjecture is focused on this interval, right? So we have some data, actually. For these values of Q, we have the exact number of A's not yielding an FQ primitive point. Okay, so I think that's it. Thank you very much for the attention.